All right, so here is part 2 of the Algebra 2 Semester A Unit 1 expressions tutorial. So in part 1, we went ahead and went over the rules or the exponent properties. Now we're going to go ahead and apply those same properties into simplifying expressions like this one on slide 19. Keep in mind we're going to use multiple properties, not just one. So we learned each one individually, but we are going to be able to combine them. So let's take a look at this first one right here. Again, on slide 19, you can follow along or pause or fast forward to through the video. Especially, I'll point out what you need to write down as notes, again, to make sure you have that prep for the practice and mastery test. It also doesn't hurt that you also follow along and write down what I write down, and to give you a little bit of a practice. But let's go ahead and take a look at this one right here. So we have parentheses, we have negative 3x to the 3 power times y all over, that is x to the 2 power. Exponents are a little too small. And this is all raised to the 4th power. So the first thing I want to do is actually remove those parentheses, but I have this 4 here. So what I want to do with that 4 is pretty much distribute. Now remember, this 4 is going to get distributed to everything inside the parentheses here. So this 4 will go to this negative 3. It will go to this x third. It will go to this y, and it will make its way here for this x squared. So I like to kind of break them into little sections. So the first thing we have here is negative 3. So I'm going to put that in parentheses. And the reason for that is because it has a negative. It was just 3, I would have write 3. Now keep in mind, there is a power here. And remember that connection when you are trying to distribute in here. If this already has a power, you pretty much multiply. 1 times 4 is still 4, so it didn't make any changes. X to the 3rd power. So again, that rule of distributing this 4 on the outside into here, you're going to multiply that 4 and that 3. So this will be x to the 12th power. Then this y, again, the y has an invisible 1. You multiply 1 times 4, it would be y to the 4th power. So then let's go ahead and continue this x squared. So down below in the denominator, 4 times 2 gives us x to the 8th power. So now that we've already broken it out of its parentheses, I'm going to focus them on little sections. So I like to color code, and we're going to try to figure out if we can do anything right there for that moment. So negative 3 to the 4th power, again, that's just saying it's negative 3 times negative 3 times negative 3 times negative 3. And if we do that, well, and I like the rule too, is that if it's an even power and you have a negative, it's going to be positive. 3 times 3 is 9, times another 3, 27, times another 3, it's 81. So we have 81 here. Now let's move on to the next part. And I'm going to break them into little sections. I have x to the 12th power here and x to the 8th. So remember, since we are dividing, again, I can write it out the long way and say, all right, write 12x's at the top, 8x's at the bottom. But the rule is that because they're dividing, we can simplify this because it has the same base. So remember, I take the exponents like a little balloon, and it's attached to the x of the base. So here it'd be, oops, let me change back the color. This is x. Remember, it's top minus the bottom. So here you'll have 12 minus 8. And then we'll simplify that for it to be 4. And the next thing is y to the 4th. There's nothing more to combine with y to the 4th. So we'll just write it as y to the 4th power. So let me remove this kind of stuff here. So here, this whole expression simplifies down to 81 x to the 4th power y to the fourth power. And that's applying those rules that we learned in slide 18. So if you think about it, we use the power of we use the power of product, power of a power, our quotient of powers, and also a combination of power of a quotient. So we use multiple properties all applied to this same one here. So we click over here on the orange button, they have a full breakdown of exactly what they did. Again, they distributed that 4 outside from the parentheses to break it apart. And now everybody got its own 4. And we start to continue to simplify. So power of a power, and then they did quotient of a power. So just keep that in mind. Let's go ahead and take a look at this one together on slide 20. So rewrite this expression in simplest forms. So I have 2 sets of parentheses there. And again, I like to break it apart, and you're going to kind of notice that I like to color code a lot of this. Color coding just kind of helps us organize this. So we have 4v to the third power. We have w parentheses. Now ask yourself this: if it has a set of parentheses, is there anything I need to do to it that's considered outside of it? And you can see it's not raised to a power. I don't have nothing to distribute into this one. So we might just be able to ignore those parentheses there. But let's take a look at the second part of this. It's negative 2w to the third power, all the way raised to the 2 power. So this set of parentheses has this 2 outside. So I want to somehow break this apart away from it. So what I'm going to do is I'm going to break this up like I kind of wrote it out into different parts. I have this part and I have this part. So the first part, there's really nothing to do. So I'm just going to write it out as 4v to the third w, plus it's all multiplying. There's no addition sign there. So we can just write it as is. So it'll be 4v to the third power times w. Now let's handle this one here. Now remember, this 2 will get distributed to this 2 and to this w to the third power. So I'm going to rewrite this as negative 2 to the 2 power, and then w to the third power raised to the 2 power. So again, we can still simplify here. Again, nothing happens to this 4, so we'll leave it like that. V to the third power. Then there is w. Now negative 2 to the 2 power. I was just telling me it's negative 2 times negative 2. That should give us 4. And to distribute this 2 into the 3, we need to multiply. So 3 times 2 is 6. So we have w to the 6th power. Keep in mind, everything in here is being multiplied. So I'm going to rearrange it so we can kind of put pretty much like terms together. So this 4 and this other 4, I can put them together like this. Not for 44, let me write our multiplication symbol. So 4 times 4, we have v to the third power. Again, they're all multiplying. I have this w and this w to the 6th power. So I'm going to say w and then w to the 6th power. So the first thing we can do, again, we break them up into little parts, right? Let's take care of these numbers first. 4 times 4 should give me what value? So I'm going to leave a box right there. And then I want you guys to go ahead and multiply it. V to the third, there's nothing that I can combine with v to the third. So this is what I meant by color coding. 4 times 4, let's change the other color. This is the only thing I see with the v, and the rest I see are with w's. So the purples are being combined for this box right here. Again, all you got to do is multiply 4 times 4 and write that answer inside. You don't have to write a box, but I left it as a place there. Now v to the third power, there's nothing else in orange, so let's put v to the third power. Then it's w times w to the 6th power. So when we're multiplying, right, this w has an exponent. It's invisible 1. So this is going to be w to the, remember we add these two exponents together because I have a w and a w, I just want one w. So 1 plus 6 is 7. So go ahead and make sure you enter that down below. It'd be 4 times 4, which you'll give me that value, or you'll type in that value, v to the third, and then w to the 7th power. So again, if you have any trouble typing it in, I'm leaving that empty space for, that's your value that you're going to enter for 4 times 4. You'll type in v, and at the top left corner, if you count off from 1 to the 4th button away, you'll click on that, type in your 3. Make sure you bring the cursor down, because if you bring it back up, you're going to type it into the exponent part. So you want to make sure you move the cursor over, type in your w to the power of 7. So remember, you're not going to fill it in as an underscore. You're going to go ahead and actually place a value for me there. Moving on to slide 21. So we do have more properties of exponents. The zero exponent is another property. Remember, anything to the 0 power is just 1. We will have an opportunity that we are going to deal with negative exponents. We don't like to deal with negative exponents, so we most likely will try to convert them into a positive. So let me again provide an example of how we would see that. So a to the negative m power is what the property is saying. And if you think about it, to get this negative m into a positive, you do 1 over a to the m. So this is technically above a fraction line. So so when you see a negative exponent, you're gonna see, what is it attached to? What's the base? And you're gonna consider, is the base above the fraction or is it below? And you're going to take it to the opposite side. So this one right here, a to the negative m, is currently at the top of the fraction. To make negative m into a positive m, you need to bring it below. Vice versa. If it is below the fraction, you need to bring it to the top and you convert the sign. So again, let me provide you like just a little example, right? So this will be 3 to the negative 2 power over x. So let's just say x to the 5th power, since we're dealing with exponents here. Okay, so I'm going to take it piece by piece again. And I'm going to take a look. 3 to the negative 2 power, I have a problem with because I don't like to see a negatives. So I'm going to have my fraction. Now, 3 to the negative 2 power, I can, if this is above the fraction, again, we need to move it to the opposite. So this is at the top. Now it moves to the bottom. So this will be 3 to the 2 power. Now, what about this x to the 5th power? I have a positive 5. I like positive 5. It's not a negative. So I'm going to leave it as it is. So this x to the 5th power will stay down below. So our fraction kind of looks a little bit weird, right? Because we don't have a number at the top. If everything disappears from the top and it goes to the bottom, you put an invisible 1. And then you can simplify this even more. It'd be 1. 3 squared is 3 times 3, or 9, x to the 5th power. So that is how we're going to do our sign flips. But I do want to give one more where we kind of use it in the opposite direction here. So I'm going to have 4 x to the 3rd power, y to the negative 2. So again, I'll draw my fraction line. I have this 4. The 4 is nice. We don't need to change it, so we keep it up here. X to the 3rd power. We like x to the 3rd power. The 3 is positive, so we keep it where it is. Y to the negative 2 power. We have a problem here. So y to the negative 2 power. I don't like that negative 2. So currently, it's at the bottom of the fraction or the denominator. We need to move it to the top, the numerator. So this y to the negative 2 becomes y to the positive 2. So that's an example of how we would switch them. Again, it's only for negative exponents. Did you see everything else kind of stayed the same except for the position of any negative exponents. Let's go ahead and take a look at this one of rational exponents. So when we are dealing with the square root, let's say the square root is 16. If we enter that to the calculator, we know that that's going to be 4. I can write the square root of 16 in exponent form. This is 16 raised to the 1/2 power, which is also 4. So another way to double check this, if you still feel like unsure of it, you can go ahead and type into Google Desmos scientific calculator, and like that's like my top fave, super user friendly scientific calculator online. So where does this 1 and 2 come from inside the square root? This 16 is raised to the 1 power, and just square root itself, it has an invisible 2 written out for there for me. So I'm going to give you the other formula that you can write by this, but again, you should write out all of this here. But I'm going to give you another addition to adding the rational exponent. So it's going to be a to the n over m, which is equivalent to m root of a to the n power. So not only are you going to be able to look at it as with exponents, but you're going to be able to, if you have a fraction exponent, it is a giveaway that it's going to be written in some type of radical form. So keep that in mind. Again, make sure you have that note listed next to that rational exponent. And let's go ahead and take a look at slide 22. So let's go ahead and rewrite this exponential expression. It's like I have to squint because, all right, so this is 9g to the 2 power. This is h to the 4th power all over 12 g to the 0, and then h to the negative 7. So one of the things I like about math is that we can pretty much break this up into pieces. There's multiple ways about going this, but I'm going to break it down just a little bit more in, like I said, color code. I'm going to break this up to, we're going to take care of the 9 over 2. We are going to take care of the G's because they line up perfectly with each other. And then the H's. So let's go ahead and take a look at this first. So like I said, there is 2 ways to do this. First way is that if you see any negative exponents, just go ahead and get rid of it, or not get rid of it. You can't get rid of it. You have to move it in order that's the correct way. You have to move the negative exponent either from top to bottom or bottom to top to make it a positive. But let's try to simplify it first before we do that. So I have this 9 over 12 that I'm going to focus on. So we can kind of, like I said, break them up into pieces. So 9 over 12, 12 can't go into 9, but we know that they are divisible by 3. So we divide top and bottom by 3. 9 divided by 3 is 3. 12 divided by 3 is 4. So I found my pink section. It's 3 over 4. What about my G section? So remember, the rule is when you're dividing and you have the same base, you do the top exponent minus the bottom. So if I take care of my G's here, this is G, and the top exponent is 2 minus the bottom one, which is 0. So 2 minus 0 is still 2. So this is G to the 2 power. Now let's go ahead, again, they're like separate sections. Let's take care of the H. H has the same base of H, but it's going to be 4, top exponent, minus, so it's always minus, the bottom exponent is negative 7. So from here, I have this double negative, so I can transfer this minus and change the sign here. So this is becoming 4 plus 7, which is H to the 11th power. So now I'm going to take each piece and put them all together. So this can simplify down to 3 over 4 G to the 2nd power h to the 11th power. Keep in mind, it can also be written out like this, 3g squared h to the 11th power over 4. Both both expressions are exactly the same, just looks a little different. So again, you want to make sure you combine those same bases. You don't want to write g twice, you just want it once. um, Again, do you see we didn't even, I could have in the beginning taken care of this h to the negative 7th power, right? Because if I look at all my exponents, this is my only negative one that I had a problem with. And like I said, we don't like negative exponents. So we could have, if this is at the bottom of the fraction moves to the top, do you see we still got the same thing? Because if this 7 up, h to the 7th went up here, plus times h, or h to the 7th times h to the 4th, it'll give us h to the 11th. So it doesn't make a big difference, but that you could have done, like I said, you could have taken that negative exponent and then changed it first. So, oops, let me just click through it here. So they did, so here, if you take a look at their example through Edmentum, here, let me clear this up, they took the 0 power. So that g to the 0, they automatically changed it to 1. So the idea here is that you can break it up into multiple different ways of like simplifying this expression. It's whichever works for you. So besides doing that g to the 0 power, they also converted that negative 7th and they brought it up to the top. Then they continued to simplify. Again, there you can follow their way, or you could have done it similar to what we did first. I like to break them up into sections. Moving on to slide 23. So what we're going to go ahead and do is before we simplify radicals, let's review 3 things. Convert powers with fractions and rational exponents to radicals. So if we're given a problem like this, right, 540 raised to the 1/2 power, they want to take the square root of it instead. So we just did a little conversion there. Remember, there's an invisible 2 out here and the 1 right there. Second thing is the radical symbol and the radicand. There are a couple ways to take care of this. I'm going to go ahead and use a tree diagram. So what do I mean by the tree diagram? Because what if we don't know how to take the square root of 540? And I don't think it's a perfect one either. So I like to use a tree diagram. So you take your 540 and you think of 2, and you break it down as much as you can by what 2 numbers multiply to get 540. So it doesn't, when you're following along, it doesn't have to be my way exactly. As long as your 2 numbers multiply and get back up to 540, you're good. But I'm going to go with 54 and 10. 54 times 10, 540. 54 can be broken down to 6 and 9. So I have 6 and 9 here. But 6 can be broken down to 3 and 2. Now 3 can be broken down to 3 and 1. I don't want to write the 1 there, so I'm going to circle it to stop. Same thing with the 2. It would be 2, 1. I'm just going to stop at 2. 9 can be broken down to 3, 3. So I'm going to stop there because just like we learned before, that 3 doesn't, breaking it down to 3, 1, it just makes it more work and more writing. We don't want to write a 1 there. So we already broke down the 54. Let's break down our 10. 10 can be broken down to 5 and 2. 5 can be broken down to 5, 1. Again, we want to just stop right there. And then this 2. So the idea is I'm going to rewrite the square root of 540 is equivalent to, if I take all these numbers that I circled and I multiply them all together, I'm going to get back to 540. But let's like organize it here to write them in order. But like 2, I have 2 2s, so I'm going to put a 2 here and a 2 here. And then I have 1, 2, 3, 3 threes, and then I have a 5. Now, because keep in mind the denominator is the power is 2. When we originally were given it to us, 540 raised to the 1/2 power, that 2 there. That means inside my square root, I can only take out pairs of 2. So I have 2 2s. I have 3 3s, but I can take out a pair of 3s. So by doing that, I removed a 2. Oops, I removed a 2 and I removed a 3. I don't have another 3 and I don't have another 5. So this 2 and 3 that I'm like considerably taking out of the radical, it's 2 times 3, the square root of. Now, keep in mind, I know I write them all together like a list. They're all being multiplied. I have this 3 and this 5. 3 times 5 is 15. Or I'll just write it like here first. We're just simplifying. 2 times 3, that is 6. And then the square root is 3 times 5, 15. So here we just simplified our radical. So I think, if I'm not mistaken, they decided to they broke it down similarly. Here, they did write it as 2 to the 2 power, then 3 to the 3rd power. I like to write it all out together, kind of like, again, like a list. And the reason for that is because, okay, I can see those pairs. Now moving on to slide 24. Let's go ahead and take a look at this one. So we have 11, j to the negative 3rd power, k to the negative 2 power, j to the 3rd power, and k to the 4th power. And they give you the values of -8 and 7. 2 ways to do this. You can plug in those values and plug them in and then just multiply it all, or simplify. I recommend simplifying it because you might be surprised on how much that's a lot of multiplying, and we're making it more work on ourselves. Let's try to simplify this before. So let's take a look at this one. So again, in the first parentheses, I don't have anything. It looks like I have to distribute. So I'm just going to write it as is. So 11 times j to the negative 3 power, k to the negative 2 power. And then in the second set of parentheses, again, I don't have anything to distribute there. So that would be times j to the 3rd power, and then k to the 4th power. So I know, and within the tutorial, they did convert all the negative exponents to positive first. I'll go ahead and do that way. I'll do this. Let me do it first where we're going to combine like terms, and then we'll do the second way on where we get rid of the negatives. That way you have both options, and then you can select which one you like more. So let's take a look here. By first look analyzing it, I have this 11 here, nothing to really do. There's no other constants, or I don't have any other numbers. So we're just going to leave that one green in its own bubble. Let's go ahead and take care of this. So I have a j to the negative 3rd power and j to the 3rd power here. Then the second set is k to the negative 2 power and k to the 4th power. So again, starting with the very front, I don't have anything to do with this change with 11, so I'm going to keep the 11 here. Now, when we're multiplying, if we have two bases that are the same, which in this case, the pink ones, they both have the same base of j. When we're multiplying, we can add the exponent. So we have -3 plus 3. And then we can do the similar situation with the k's. We can take the k and write it as one base. This will be -2 plus 4. So now, again, we're going to simplify this. This will be 11. -3 plus 3 is j to the 0 power. Right? -3 plus 3. -2 plus 4 is k to the 2 power. Now, remember, anything to the 0 power is just 1. So that j actually disappears for us. So then this is going to be equivalent to 11k squared. So see here, you were supposed to plug in j as -8 and k as 7. We don't have to do much here. So let me, before we plug it in, or before you plug it in, because I'm going to have you go ahead and work on that, I want to solve it the other way, meaning where we get rid of the negative exponents first and then simplify. So I'm gonna do just like a side-by-side comparison. And again, whichever way you like more, whichever way you see, go with that and go with that way. You want to do the one that's like you're more comfortable with. You get this, you should get the same. We will be getting the same result as 11k to the 2 power. So again, I take a look at my expression and I notice again, I don't need to distribute anything into those parentheses. So everything is just fine. So what I'm going to do is we can agree that this is above the fraction line. So this is like a giant new, it's like, there's like an invisible one down here as our denominator. That's our numerator. That 11 I'm okay with. So I'm going to leave the 11 there. That j to the negative third power, I have an issue with. I don't want -3. I want it to be +3. So I'm going to bring it down below. So this is j to the third power. Then it's k to the -2 power. Again, we don't like it, and it's at the top. We bring it down to k to the 2 power. J to the third power is okay. K to the fourth power is also okay. So j to the third, k to the fourth. So now if we think about it, nothing to do with that 11. Do you see the j thirds? They're the same top and bottom. Again, that just gives you one, or you can say they cancel each other out. But again, that just gives you the value of 1. If we remember our rule with quotients, it's top minus the bottom. So 4 minus 2 is 2. So we also get 11 equals, well, we'll write this as 1 base. Okay, oops, I wrote equals. No. There you go. 11k to the fourth minus 2, or that's 11k squared. So here we, like I said, we simplified, and then you plug in your values. You don't even need to plug in both. You just need to plug in one. So again, I'll go ahead and have you do that step on your own. So 11k squared. So you'll have 11, and instead of k to the 2 power, you are going to replace k with 7. So 7 to the 2 power. So again, go ahead and multiply that out for me. 7 to the 2 power, or 7 times 7, multiply your 11. That will be your final answer there for slide 24. Let's go ahead and move into slide 25. Again, don't forget that you can go ahead and pause or go back through the video, especially when you're catching up on notes. So performing operations. Let's go ahead and read slide 26. We found out that the two area expressions for Bella's patio are equivalent, but why are they equivalent? Well, remember we said if we focus down here we have this is the width, this is the length. If I distribute this W on the outside of the parentheses inside, we get the same expression. It's like that idea that I said, you say tomato, I say tomato, but we're referencing to the same thing. Now here, it looks a little different, but it's still the same expression. It's just rewritten differently. So here are a couple examples that we use for distribution. My preference would be the distribution at the top where you can draw your lines, right? I distribute this in here and this in here, and you come up with your answer. There is also box where you break up the two terms inside the parentheses and place the number on the outside. So this is, again, the distributive property, and then you have it with tiles. So here they're actually applying the tiles without, or oh my goodness, I'm spacing. sorry. The algebra tiles are for X, and then the ones, they're like building blocks. I would try to avoid this as much as possible. There are online tools that you can use as algebra tiles, but you want to stick to this, especially algebraically. You're not going to draw out the tiles every single time. But again, we'll go ahead and see that in the next one. But this same expression written up here at the top, it's written in 3 different ways. If you like the algebra tiles, you can stick to it. But do I highly recommend it? No. Um, I would like, even if you do the box, that's still fine. You just don't want to spend so much time drawing out the tiles. But let's take a look at this one on slide 28. So we're going to simplify expressions where, again, we're going to keep the like terms together and we're going to most likely distribute things. So let's take a look at this one. Now, on the orange side, you can click through it and they'll explain you the steps, but I like to explain it on my own and as we work on it together. So also, it's like I highly recommend you write it out as well and you're following along. So I'm going to block out this just for a quick minute while we go ahead and write out that top one. So I'm going to erase this piece here too. And let's go ahead and take a look. So we have -7 parentheses y squared plus 3y parentheses minus 4y, oops, minus 4y plus 11y squared plus 6. Okay. So again, you want to, you're taking a look at what you can and you can't do automatically. So it's like you're taking a look at it piece by piece, especially if you have parentheses, you want to focus on that part first. So as we read it from left to right, I already have some work that I need to do here. That -7 is sitting outside of the parentheses. We can let it in by multiplying it in. So it'd be -7 times y squared, -7 times 3y. So we write out that, if we write it out, we get -7y squared minus 21y, right? Negative times a positive is a negative. Then if we continue looking at the rest of the expression, there is nothing to really do to distribute wise. So what I'm going to do is I'm going to write the rest of this as the same thing, continuation going down here. So this is going to be minus 4y plus 11y squared plus 6. So the next part of this idea here, right, is we're going to combine like terms. I feel like this is just too expanded. I want to condense it a little bit here. So if I take a look at the first term, this -7y squared, I'm not going to look for the exact, when we say like terms, it's like which one is kind of like that. And it mainly has to do with the variable. And when you're dealing with the constants, just regular numbers with no variable. So it's like I'm looking for other terms to see what who else has y squared. So I take a look at this -21y. It's just a y. I'm looking for y squared. So I wouldn't highlight that in pink. Minus 4y, still nothing. 11y squared. That sounds almost exactly right there, y squared. And then I have this 6. Again, nothing to do there because it doesn't have a y squared. So then we move on to the next term, right? Because there's no other y squareds. This one just has a y. So, and then if I look at it, the next one has a y. That 6 doesn't have a y, so I'm going to give it its own color and let it sit there. So now we put them together. So the first thing here is -7y squared plus 11y squared. Well, I like to think of negatives and positives. It's like negatives, you owe some money, and positives, you have the money. So if you owe somebody $7 and you have $11, how much money are you left with? It would be positive 4y squared. So if you're left with money, it's going to be positive. If you still owe money, it'll be negative. The next part is the green. So do you see, I already handled the pinks away. I got 4y squared. The next part is the green. So negative 21y minus 4y, they're both negative, so we're going to keep it negative. 21 and 4 is 25y. And then, so we took care of that. Now we have this plus 6 that doesn't have anything to combine. So we just simplified our expression right here. So we're going to use, again, we're going to use a combination of distribution property. We'll be combining like terms, but we went from this super long line to, or actually, excuse me, after we distributed, if you count off the terms, we had 1, 2, 3, 4, 5. We went from 5 different terms to 3 terms down below. So keep that in mind when we're simplifying. We want to condense it a little bit. So again, they distributed and they actually rearranged it. So I know I didn't rearrange it, but I did color code it to help me organize it. Edmentum would rewrite this. So it's like an extra step that would go kind of in between here. To me, it's optional, especially if you are able to color code. I think highlighting or like using the color pencil works, but in between this step from where we colored and where I boxed our final step or our final answer, they would rewrite this. So negative 7y squared plus 11y squared minus 21y minus 4y plus 6. You can. I feel like it just reiterates, and after the color coding is another way to like organize the expression to be able to get to this final answer here. So again, it's up to you which way you like or what is your preference. I like color coding because it's colors. I didn't get to that final step on side 28. Give me a second here. So they came out with the same result, 4y squared minus 25y plus 6. Let's go ahead and move on to slide 29. So rewriting more complex expressions. So x minus 1 and x plus 4. When we're multiplying that, there are 3 different ways that they go over it. The first one is distribution property, but I have a different name for distribution property, especially when you're dealing with two binomials, because each parentheses has 2 terms. I like to call it the banana method, which I will show you right now. So when we're multiplying this, there's a reason why I call this banana method. Oh, let me get this as a white screen. My bad. So what do I mean by, why do I call it banana? You'll see right now. So it'll be x minus 1 parentheses x plus 4. Again, I have a preference. I would like for you to kind of pick up on this. It's the same thing as distribution, but I call it banana because you should come out with a banana at the end of it. So starting from the far left, which is this x right here, in front of the minus 1, you're going to distribute into the other parentheses. So we have x times x, and we'll write our answer, x squared. And then x times 4. So if you have seen this a little bit before from your algebra 1 class, you did learn it. They do have a name for it as the FOIL method. FOIL method, distribution method, they're all the same. But again, I think I like calling it banana. So it'd be x times x, x squared, x times 4, 4x. Now it's the negative 1's term because we distributed as much as we can here. So negative 1 times x is minus 1x. Negative 1 times 4 is negative 4. And I get a lot of confusion because I know my drawing is not the best, but this is supposed to look like a banana. I know I have other students that say it looks like a moon crescent, but it doesn't have the same ring to it when I say banana method instead of moon crescent method. It's too long of a word, too long of a phrase. So we're not done though after I multiply this out. But like I said, if you do this properly, you should come out with some type of banana looking figure or drawing. So in here, I have nothing combined with this x squared, so that is just x squared. 4x minus 1x is just 3x. So again, that's just the combining like terms. And then nothing to combine with this minus 4, so we have that. And this same answer is going to follow along to what they have here. So like I said, this can be, it has multiple names. It could be the distribution. It could be, like I said, banana method, or it could be FOIL method. If you're a banana, the way, if you follow the order of banana method, it is very similar to FOIL, where remember first, which is x and x, and then it is outside x and 4, inside -1 and x, last -1 and 4. Same setup when you do it as applied as a banana method. There is the box method. So you would kind of use it like a multiplication table chart and break out the parentheses. So the top of the first set of parentheses is x minus 1. You're going to bring your x, your -1, and then your x and 4. And pretty much what we do is, right, is like x times x is x squared. X times -1, -1x. 4 times x is 4x. 4 times -1 is -4. So as a multiplication chart. Now here you can write it out. You get x squared minus 1x plus 4x minus 4. Again, they circled here this green because you can combine these to get 3x. Again, that's the same answer as what we got from here. This is my tiles. So these algebra tiles represent the outside. So the algebra tiles is very similar to box method, but we're not writing out the numbers. We're using algebra tiles here. So in the box method, we had x minus 1. Here on the outside is your x minus 1, right? X, then you get this 1 and you convert it to a negative by making it red. Then you have x times 4, which is 4 x, and then 4 ones. And the idea here is that you follow the same thing. X times x, x squared. 1 times x, x. 1 times x. So you're following it like a multiplication table. And then if you have, so they have the red versus the blue. Blues are positive, red are negative. So if I have a negative x, it cancels out with a positive x. And that's pretty much the only thing you can cancel. So if I rewrite everything that I didn't cancel, I have 1x squared. So I'm going to write x squared. I have 3 x tiles available, so that is plus 3x. And then I have 4 of the -1s. That's your -4. So again, we've been getting the same answer. We're just applying it differently by multiplying. I recommend the first one to take care of. So let's take a look at slide 30. So here we are going to complete the algebra tile grid. So here it looks like this is a 1, and this is a 1, and this is your x. Again, do I want to, do you see how kind of time consuming this can be? I have -3, negative. And these are actually in red. So again, we can multiply this. Do we want to? No. Like I said, let's go ahead and try to practice using it, like I say, distribution method or banana method. So we have x plus 2, parentheses, and parentheses, x minus 3. Start from the far left with this x. X times x is x squared. X times -3, -3x. 2 times x, positive, plus 2x. 2 times -3 is -6. So if I simplify this part, this will be x squared. If you owe somebody $3 and you have 2, you still owe them $1 more, so that's -1x minus 6. Again, we can do the algebra tiles. Here you're going to get, let me see if I can draw them kind of quickly. It'd be x times x, so this is your x squared. Then you have 1x times 1x. Then this is -x, because that's a -1. -1 times x again. -1 times x here. Then it'd be -1, -1, -1. My tiles are uneven, I apologize. And I didn't mark them. So x times x, this is your x squared, plus x, negative x here, negative x here, negative x, oops, -1, -1, -1. Again, the algebra tiles is a little bit time consuming. So whatever you have, if you have the same tile that is red and blue, you can cancel it out. So I have one blue right here, or actually what I'm gonna do is I'm gonna erase it. I have a positive blue x, I can erase a negative x. Another blue x, I have another negative x. And if I take a look, can't cancel out anything else. So I'm left with x squared, which is right here. There's my negative x, because I have one tile of that. And then I have 6 of the -1 tiles, or -6. So again, represents the same thing, but this is a little bit more time consuming. So when you're entering the answer down below, you're writing out the coefficients. And remember, if there is no number listed, it is an invisible 1. So 1x squared, that would be a -1 here. Oops, negative. And then it'd be plus -6. So this is just 1, -1, and then we have our -6 here to enter down below. Let's move on to slide 31. So factoring out the expressions. So we just learned or reviewed how to multiply these using banana method. What about if I want to break them apart? Or again, factoring out an expression. So we're going to be factoring out the greatest common factor. When I take a look at this, you pretty much you go from playing with parentheses to get rid of them. You want to go reverse. You want to have parentheses. So I take a look at w squared plus 5w. Again, there's two ways to solve it. You can kind of see this is one term, again, this is the other, and be like, all right, they both have a w, so let's try to take out a w. If I do that, this is no longer w squared, it's just w plus, I remove this w here, w plus 5. And that's exactly what we started with. If I use distribution property, I get back to the top. So they all kind of wrap in with one another to each other. Let's take a look at slide 33. So we are going to factor out here this quadratic. We want w squared plus 7w plus 6 to pretty much look like this, parentheses times another parentheses. Now, if I think about it, I'm going to do this giant X. So this is what we factor. And this is, so let me kind of color it. This right here at the top is used when you are going to multiply this value right here and the value in front of w squared. So keep in mind, remember, that is just a 1 there. So 1 times 6 is just 6. And I'm going to put the little multiplication symbol there. And then the bottom part of this giant X, so right here, again, this is all coming from this right here. So this does have a normal setup of a formula, or not a formula, and as set up as an expression where it is a x squared, oops, ax squared plus b of x plus c. And for the giant X, you at the top of the giant X, you put a times c, and you place your b down below. So your b here is in orange, that's your 7. So I have my 7. You want to list the multiples for 6. And again, this is for the adding, because you're going to put a number here and here. So the multiples for 6, right? Because you're multiplying. We started out with 1. 1 times 6 is 6. After 1, it's 2. Can 2 go into 6? Yes, it can. It can be 3. After 2, it's 3. Do you see how I go back to 3, 2? I already have the same pair. I don't need to write it anymore. So now that we talked about the multiplying part, let's talk about the bottom part, which is the adding. Which pair, right? Is it 1, 6 or 2, 3 that can give you the 7? In this case here, because sometimes you will be dealing with negatives, you might be needing to add or subtract them, and you can change them by putting in a negative. But again, when you read it off, it needs to make sense. So here it is 1 times 6 is 6, 2 times 3 is also 6. But 1 plus 6 is 7, 2 plus 3 is 5, or the difference is 1, and the difference here is 5. So let's just put our 1 and our 6 here. 1 times 6 is 6 at the top. 1 plus 6 is 7. So I have this positive 1 and positive 6. My factored form is x plus 1 and x plus 6. So this, when you're factoring these expressions, going to take a while to get used to, but the giant X will not always work. It works in most cases, but sometimes it's not always going to work. And then we have to refer back to some other different methods to factor. So here they are bringing it back to kind of like the algebra tile that we learned when we were like distributing, where they place w squared here, and we know that that comes from w times w. Oops. So I know I wrote it here as x, force of habit. That should be w's, my mistake. Oops, w and w. And then here we know 6. The question is, do you see, they wrote out the factors for you, kind of like how I wrote them out here at 1, 6, 2, 3. The thing is, right, you want to get that 7. So this is their way of the giant X. I think it might be organized again. It's up to you. But I like the giant X. But like I said, the giant X will not always work for this type of thing. So let's talk about grouping, which you can kind of use a giant X as well, very similar to it. So let's go ahead and focus on that. So when I look at expression A, negative 4x squared, 28x minus 40, I can kind of see that each term is divisible by 4. And not only that, the leading expression, the number in front of x squared is negative 4. I'm going to factor out a negative 4 from there. So when I factor out negative 4, I'm going to put parentheses, right? X squared. Because I factor out a negative, all the signs change. So this goes from negative 4x squared to positive x squared. Plus 28x becomes negative 20. It will no longer be 28. 28 divided by negative 4 is negative 7x. Negative 40 divided by negative 4 is positive 10. So we just factored this. I can factor even more. Inside the parentheses is telling me that I can set it up for a giant X. So I put my giant X here. Remember, I like when this x squared has a 1 in there, because all I got to do is just write 10 times 1 is 10. And then this negative 7 down here. So let's see. Multiples of 10 is starting with 1. 1 times 10. 2 times 5. 3 doesn't work, so we go to 4. 4 does not multiply into 10, neither of 5. We're back to this. Which pair can give me negative 7? So if we play around with 110, I can get either 9 or I can get 9 or 11. That doesn't give me negative 7, so we're going to erase that. 2, 5. If I add those two together, I can get 7, but I want negative 7. So in this case here, this should carry the negative, so will this. So negative 2 times negative 5 will give me positive 10. Negative 2 plus negative 5 is negative 7. So now that we have it, I can rewrite the inside of this parentheses as I still have this -4 at the bottom. So this is -4 x minus 2. So when it is a negative, you just represent it as a minus. And then this is x minus 5. And we're done. If you were to use banana method and then multiply the -4, you would get back up to here. Again, this is just factored more. Now let's take a look at the next one, expression B. So expression B is, so let me rewrite this again. So I'm going to rewrite the formula it's originating from, or like the setup of it. Ax squared plus b of x plus c. Where if it might actually be helpful if you identify your ABC first. So you have 6h squared minus h minus 12. So if you can kind of see, they line up with the ABC. This is your A, this is going to be your B, and this is your C. Keep in mind, if there's no number listed there, it's just a 1. In this case, it's going to be -1. When you have a minus, it's going to be represented as a negative number. So here, remember the setup for the giant X. So we're going to use a giant X, but it's going to be used a little bit differently. It's A times C at the top, and then you just place your B at the bottom. So here we are going to multiply 6 times -12. So 6 times -12, what? That's 72, -72. And then we have -1 at the bottom. So here we're going to go ahead and just multiply. Starting with 1, right? Because we're going to write out the multiples for -72. Keep in mind, I know it's -72. Do I have to write out the negative numbers of it? Not really. I always write out the positive. So let's start with 1. 1 and 72 make 72. 72, 2 goes into it. It'd be 2 times 36. 3 can go into it, but that is 3 goes into 7 2 times, 12, 24. This might give us a longer list, so 4 and 18 work. 5 will not work. 6 will work because that is just 6 and 12. 7, no. 8 will be 8 and 9. After 8 is 9, we're back to this here. So now we do have our list. It's a little bit longer, but I want to try to get a 1 from here. So like I said, you can add or subtract. 1 plus 72 is 73, and if I subtract them, I get 71. That's not close to 1 at all. 2 and 36, either 38 or 34. 3 and 24, again, the difference between them is too high. 4 and 18, you can either get, that is 22 or 12, or 12? No, 12 and 14, my mistake. Again, I'm just adding or subtracting them. 6 plus 12 is 18, or minus them, you get 6, that's still not 1. 8 plus 9 is 17, but if I subtract them, I'll get 1. So I'm going to place my 8 here, and I'm going to place my 9. Again, I need to multiply these two to get a negative number here at the top. So I'm just going to place a negative here first at the top and see if it works. -8 times 9 is -72. That works. -8 plus 9 is not -1. It's +1. So here, the negative is actually not where it's supposed to be. Let's try with 9. 8 times -9 is -72. 8 minus 9, -1. So this, again, it is very different from how I wrote, how I'm going to use it for expression A. But I am going to rewrite this. So I'm going to use this 8 and negative 9 and replace your b here. So I'm going to have 6h squared. This piece will be replaced with the numbers I have here. So this is plus, or let's just do, oh yeah, plus 8h minus 9h minus 12. So what we're going to do is, well, we just made it larger. Why would we want to make this larger? We're going to be able to group factor by grouping. So at 3 terms would normally suggest for a giant X, but because we don't have the A value is in 1, that makes it a little bit more complex for us. So we use the same steps, but we apply it differently after. Here, you're going to group the first 2 terms, and then you're going to group the last 2 terms. And you're going to factor, or you're going to take out the GCF. So I focus on the first set of parentheses. 6 and 8, they're both divisible by 2. So I'm going to factor out a 2. And they both have an h, so let's take out an h. So I factored out 2h. That's going to give me 6 divided by 2 is 3. This tells me I have 2 h's because it's squared, right? Because h times h. If I took away an h, I'm left with only 1. So that is 3h plus 8 divided by 2 is 4, and I took away their h there. Let's take a look at the second set of parentheses. What can I factor out from there? I see a negative 9 and a negative 12. Keep in mind there's like a little plus sign there. My bad. I can factor out a negative 9 and 12 are both divisible by 3. So I'm going to put negative 3 here. And let's see. Negative 9 divided by negative 3 is positive 3. We have h. And negative 12 divided by negative 3, positive 4. So do you see here how 3h plus 4 and 3h plus 4, same thing. So I'm going to write out what I have in blue because I'm going to remove this. So if I remove it, let me just write it out here. There's 3h plus 4. I still have what I have left over for blue, which is 2h minus 3. So we use the giant X again, but we apply it a little bit more different. That is your complete factored by grouping. Like this one was a little bit different here. I saw that they were all divisible by 4, so that's what we wanted to push for. The other one wasn't divisible by 4, so that's why we had to change it there. So here they're doing, again, the same thing, but they're solving it just a little bit different, but you can go ahead and pause the video and take a moment to review what they factored out for you here on slide 35. Let's take a look at slide 36. Factor each expression, factor this expression. Okay, so they kind of already give us a hint. It's going to be 3x times x, which is 3x squared, but we need to find that missing number. So again, I'm going to apply just a giant X. So I have my giant X here. 3 times negative 20 is negative 60. And then I have negative 11 at the bottom. So multiples for 60. I have 1 and 60. After 1, there comes 2 and 30. 3 and 20. 4 goes into 6 one time. 24 and 15. Then it's 5 and 12. After 5, it's 6 and 10. After 6, 7 won't go into 60. Neither does 8. Neither does 9. And then 10 back to 6. Okay, so we made it through the list. Which one can give me negative 11? 1 and 60, the difference is too high. 2 and 30, no. 3 and 20 is 23 or 17. 4 and 15 is 19. But if we subtract them from each other, we get 11. So there's our numbers, 4 and 15. And now the thing is, who carries the negative again, right? If I put this to my -4, I know -4 times 15, -60. -4 plus 15 is -11. Is it negative? Or actually, it's not -11. It's +11. So the negative doesn't work there. It works better for the 15. So here, again, remember, I can't rewrite this again, or can't just write as 3x plus 4x minus 15. I have to rewrite the whole thing. So this is 3x squared plus 4x minus 15 x minus 20. So what we're going to go ahead and do, we're going to group them. So here I have this first set, and I'm going to factor that negative inside there. So there's a little plus sign in between. So I can't factor out anything from 3 and 4. The only thing I can factor out is an x. So I'm going to factor out x, and let's see what we're left with. We have 3x plus 4. And then here I see two negatives, so that's a negative there. 15 and 20 are both divisible by 5. So let's just say 5. There's no x to factor out because that 20 doesn't have an x. So then we're left with negative 15x divided by negative 5, positive 3x. Negative 20 divided by negative 5 is positive 4. Again, we're left with that same thing. 3x plus 4, 3x plus 4. And then this is x minus 5. So then here, 3x plus 4, x minus 5. So let's go ahead and move on to slide 37. Or actually, we just made it to the end. So please make sure you pay attention to the summary. You saw a little bit of everything, right? You saw like verbal descriptions of an expression, evaluating expressions, meaning like here's an expression and I give you the numbers to plug in for each of those variables. We went over properties of exponents. We went over orders of operation. We went over a lot of different material, and then also factoring. But again, it is a review from the Algebra 1 class. So go ahead and make sure you click all the way through and head into the practice and mastery test.